Hello everyone, my name is Sajjad Muslihi. In this video I'm going to talk about modeling of fluid flow and heat transfer in porous media using the MATLAB Reservoir Simulation Toolbox, or MRST. So for this video I used a particular script in MRST, which is already available for you on um, this website or in the package of MRST, and it is in the book module, which is here. So you can use it and change it in any way that you want it to be. Of course, I have changed it a little bit to make sure that it is going to be easily understandable for you. So um, the porous medium that I considered is a single porosity porous medium, so it doesn't have any fractures. And the fluid that I'm going to have in this porous medium, and I'm going to inject in this porous medium and also produce, is water. And this water is considered as a slightly compressible fluid. I need to mention this because sometimes we consider water as an incompressible fluid, because sometimes its compressibility is even less than rock. So we can consider it as an incompressible fluid. But here I considered water as a slightly compressible fluid. So it has some compressibility, but a very, very low value. And so when the pressure changes, its density changes a little bit. And it is considered in this simulation. And the boundary conditions are a production well, an injection well, which I sometimes call internal boundary conditions. And the external boundary conditions, or the conditions that we have at the external faces of the domain or the grid, are no flow boundary conditions. So we don't have any flow at those external boundaries. But we have a production well and injection well in this porous medium. So first of all, what we need to do is to define and discretize the domain. We could have a one-dimensional porous medium, or any more dimensions that we want. Here we have 10 cells in the x direction, one cell in the y direction, and one cell in the z direction. So it's a one-dimensional domain in the x direction. And the total length of the model is 5,000 feet, and the total width is 10 feet, and the total height is 10 feet. But this 10 feet is the size of this single cell. But for this one, it's different. It's 5,000 feet for 10 cells. And so each cell is 500 feet. All right. So we put these values, the number of cells in each direction and the total lengths in each direction, as the input argument. We consider them as the input argument of this function. And this function calculates the properties that we need to have for our simulation later. For example, the volumes of the cells and many other data that we need to have for example, for the calculating the transmissibilities and things like that in an unstructured way. Of course, for the calculation of, for example, the volumes of the cells, we need to pass this variable to this function, and then this function calculates the volumes of the actually cells, or the grid cells of the grid, and some other additional information about the grid. All right, so let's take a look at the domain. I know that it is already clear to you what it looks like. So this is our domain. Of course, certainly the dimensions are not real, because as you see, the size of the domain in the x direction is much uh, actually larger than the other dimensions. So if I want to take a look at the domain with real lengths, I should write axis equal height like this, to make sure that uh, the lengths are real. So this is actually the actual um, sizes of the domain, but as you see, we cannot easily see the grid cells. So I sometimes remove this to easily see the grid cells and the colors on them very easily, particularly when we want to see the pressure profile, the pressure data, and the temperature data on the grid cells. All right. So now it's time to specify the properties of the rock that we have. Here we have specified the rock permeability, the rock porosity, and some other data that you are already familiar with: rock compressibility, the uh, coefficient of isothermal compressibility of rock for the calculation of the pore volume as the pressure changes, and the initial pressure of the reservoir is 3,000 psi, which is considered as the reference pressure for this function. And for the energy conservation equation, we also need to actually have some data about the rock. For example, we need to have the rock density, the rock specific heat capacity, and a function for the calculation of the volume of the grains of the rock. All right, the matrix of the rock, the grains of the rock, not bulk. I'm referring to the grains, not bulk of the rock. Okay, so later you will see that I need to have this volume, the volume of the grains of the rock, in order to calculate, for example, the internal energy of the grains of the rock. So for you see the energy conservation equation here, and as you see, part of this, the accumulation term, is the grains, right? The grains here. And so for this part, we need to have the density of the grains and also the volume of the grains. The volume of the grains. This is for the next time step, or the current time step, and this is for the previous time step. And I'll talk about this later. So some data about the rock. Here we have a function, an anonymous function, to calculate the rock internal energy, which is calculated in this way: the multiplication of the rock specific heat capacity and the rock temperature. All right. So now it's time to define and specify some info about the fluid that we have, which is water, the viscosity of water at the reference temperature. What we have done here is, we want to define a function for the viscosity of water. So we need to define some actually parameters for this function. So you could use any other correlation that you want depending on the fluid that you have. If you have water, you can use this correlation, which is actually located in the geothermal module. If you have, for example, CO2 in your porous medium, you need to use a different correlation for the calculation of viscosity in that system. So this is for viscosity, which is a function of pressure and temperature. And this is another anonymous function for the calculation of density of water as a function of pressure and temperature. And here I have specified the properties of water for the energy conservation equation. The specific heat capacity of water at constant pressure is set to this value, and we have defined here two anonymous functions to calculate the water the water enthalpy, specific enthalpy, and also the calculation of water internal energy. And for internal energy, we need to subtract. Actually, we need to do this, the water enthalpy minus pressure over density. And this gives us the water specific internal energy. So for the calculation of water enthalpy, we can, for example, use an equation of state or something like that that you have access to. But here I have used this function, which is the same function that is used here. All right, so here, as I have already talked about in the previous videos, I have computed the transmissibilities, but for this simulation, in addition to the calculation of transmissibilities for the fluid, we also need to calculate the transmissibility for heat. So in this way, the heat transmissibility is calculated, and to do this, we need to specify and we need to have the conductivity, the thermal conductivity of water and the thermal conductivity of rock. And then what we do is to calculate the average or the bulk rock conductivity, in this way. So what we do is that we multiply the grain thermal conductivity. You multiply the grain thermal conductivity by the grain volume plus the water thermal conductivity by the pore volume of the rock that we have. So in this way, we calculate the average thermal conductivity of the rock, and then we use this conductivity for the calculation of heat transmissibility. And this heat transmissibility is used for the conduction term in the energy conservation equation. And as you know, we have two actually, let me talk about it later. But for the transfer of heat in porous media, we usually consider two terms. One is the advection term, which I sometimes call the forced convection term, and also there is another mechanism that contributes to the transfer of heat, and that is the conduction term. And I'll talk about and I'll show you these terms later in this video. All right, so what we do here is to get some operators, and these operators will be used for constructing and writing the residual equations that we have. The residual equations in this simulation are a pressure equation, which is the mass conservation equation of water, and the energy conservation equation. So we have two residual equations, or we have two governing equations, all right? And for writing those governing equations, we need to have these operators. In MRST, we use these operators for writing the governing equations. But if you're if you want to write the governing equations in another software tool, maybe the approach is different. But in MRST, you use these operators in order to write the governing equations. So Now it's time to specify and calculate the initial pressure and temperature in our porous medium. I'm not going to go through all of that. I think it's already clear. Um, so yeah, this is the initial temperature in the porous medium, and this is the initial pressure in the porous medium. So even if our porous medium is has a dimension in the vertical direction, in other words, if the number of cells in the vertical direction is more than one, in that case, this also calculates and this also considers the geothermal gradient for the calculation of initial temperature. And it also actually considers the pressure gradient that we have in the vertical direction for the calculation of initial pressure in the porous medium. But for this case, that we have a one-dimensional porous medium in a horizontal way, so we don't have any temperature change in actually this porous medium because there's no movement in the vertical direction. And we only have one cell in the vertical direction. So the temperature doesn't change in the vertical direction and the pressure doesn't change in the vertical direction. In other words, actually, we don't have any vertical direction for our porous medium. All right, so now it's time to add some boundary conditions. As I said before, the external faces of the porous medium have no flow. So we have no flow boundary conditions at the external faces of the porous medium, but we have two internal boundary conditions, which are a production well and injection well, and we define them in this way. You already know how they're defined. The injection rate is this, and the bottom hole pressure of the production well is this value, and the bottom hole temperature of the injection well is this value. All right. Now let's take a look at the wells and also the initial pressure and temperature values in our porous medium. All right, as I told you before, because our porous medium is one-dimensional in the horizontal direction, we don't have any pressure, change, and also temperature change in our porous medium. So we can also see the injection and production wells. The injection well is located in the first cell of the domain, and the production well in the last cell of the domain. All right. In this section of the code, we have specified the total simulation time, which is about 1 year. And here we have calculated the time step size, which is the same value for all the time steps that we have for the simulation. And here we have specified the info of the solver, which is the Newton-Raphson nonlinear solver. This is the Newton-Raphson tolerance, and this is the maximum number of iterations that it could take. Here we have initialized the primary variables, the pressure values. Certainly pressure is a primary variable in this system. And we also have an energy conservation equation. So we need to have, we have actually a primary variable for it. So actually I should say it in the opposite way, because we have temperature as an unknown in the system. We need to have an equation for it to solve and to calculate the temperature values. And for that, we have the energy conservation equation, all right? So the primary variables are pressure and temperature. We initialize them in this way, and we store the initial conditions in this struct, and here we start the main simulation for loop. All right, so I'm not going to talk about these. I already talked about them in the previous videos, and All right, so let me talk about the parts that are related to this video. Here we have calculated the properties of the rock and fluid that we have. Uh, Here we calculate the density of the fluid for the current time step and for the previous time step. And here we calculate. Of course, we don't calculate this. It is already known. The density of the rock, and as you see, it is the same value that we specified before, and it is not a function of pressure and temperature because it's the density of rock doesn't change that much, and so we assumed that it's a constant value. All right, so here we have calculated the viscosity of water for the previous time step and the current time step as a constant of pressure and temperature. Here we have calculated the pore volume of the rock, the solid volume or the volume of the grains of the rock, the enthalpy of water, and the internal energy of water, which are specific values. This is the specific enthalpy of water, and this is the specific internal energy of water. And here we have calculated the specific, oh sorry, I think, yeah, I made a mistake here. This is the internal energy, not enthalpy. The specific enthalpy of water is this, and the specific internal energy of water is this. This one is for the current time step, and this one is for the previous time step. All right, so now that we have all the parameters calculated, we can write the governing equations. But for the pressure equation, we first need to calculate the volumetric flow rate. So here we calculate the actually difference between the centroids of the grid cells in the vertical direction. Why we need to do this? Because we need to have it for the calculation of gravitational forces in the Darcy's law. So this is the pressure forces, and this is the gravitational forces in the Darcy's law for the calculation of the volumetric flow rate. So what you see here is the Darcy's law, and this is the water transmissibility, which is divided by the water viscosity and multiplied by this potential term. And it will give us the volumetric flow rate. All right, so we use this volumetric flow rate for the advection term in the pressure equation, which is the mass conservation equation of water. What you see here at the beginning of the pressure equation is the accumulation term of water, and this is the advection term of water, which accounts for the inflow and outflow of water, into the grid cell that we have or out of the grid cell that we have. All right. So this is the advection term, and we are done with the pressure equation because we don't have any component. We only have a single component, right? And that's water. So we don't need to have a diffusion term. All right. When do we have a diffusion term? When we have more than one component, right? When, for example, when we have a particular component, for example, the calcium cation in water. In that case, we could have diffusion, molecular diffusion. But because in this case, we only have a single component, we don't have any diffusion at all. So I have not, and we don't need to have a diffusion term for the pressure equation. And we also have the energy conservation equation, which is used for the calculation of temperature values in our porous medium. So this is the energy accumulation term. what we see in the first part of the accumulation term is for the current time step, and this is for the previous time step, which is actually the definition of the accumulation term, right? The energy of the current time step minus the energy of the previous time step. So how is the energy calculated here? We multiply the pore volume of the rock by the density of the fluid in the pore volume, which gives us the mass of the water, and then we multiply this mass by the internal energy of water, and this gives us the energy of water in the pore volume of the rock. But you know that we also have rock in addition to the fluid that we have in the porous medium. So we also need to calculate the heat and the energy, let's say, in the grains of the rock as well. So in order to do that, we calculated the volume of the grains of the rock before, and we multiply this volume by the density of the grains of the rock, which gives us the mass of the grains. Then we multiply the mass of the grains by this actual parameter, which is the specific internal energy of the grains that we have. All right. So all the terms that we have here, ER, EF, are specific terms. What I mean by specific is that it is energy divided by mass. All right. That is the definition of a parameter which is specific. All right. Great. So, as I said before, this is the accumulation term of energy, and what we have here is the actually energy advection term. So, what is done here is that we multiply the volumetric flow rate of water by the density of water, and then we, which gives us the mass rate of water, and then we multiply the mass rate of water by the specific water enthalpy, which gives us the inflow and outflow of energy, all right, or energy rate, all right. And this energy rate, this gives us the energy rate at all the faces of the grid cells that we have, and by the usage of the divergence operator, the net inflow or outflow of energy is calculated for that grid cell, which is the same as this one, all right? And for this energy conservation equation, we also have the diffusion term, which for the energy conservation equation, we usually call the conduction term, all right? So we didn't have diffusion for the pressure equation, but we have it for the energy conservation equation, all right? Because we have a temperature gradient in the porous medium, and that temperature gradient results in heat flow and heat transfer, and we need to consider that in porous media. If we are in a pipe, we may ignore it because the effect of actually heat advection is very, very large compared to heat conduction. But in porous media, heat advection is not very much. Why? Because the velocity of fluid in porous media is low. So we need to also consider the effect of the conduction term on the temperature profile in porous media, or in the temperature distribution in porous media. All right? Great. As I said before, this is the conduction term. What we have inside this divergence operator is the multiplication of the heat transmissibility and the temperature difference. So this gradient operator does not give us the gradient of temperature, but it gives us the temperature difference between the neighboring grid cells that we have. All right, so the name is a little bit misleading, but yeah, what it actually does is to calculate the difference in the temperature of the neighboring grid cells. But the actual meaning of gradient is, for example, the difference between the temperature of two grid cells, divided by the distance, between those two grid cells. All right. Yeah. So in this way, the heat rate due to conduction is calculated at all the faces of the grid cell, and this divergence operator calculates the net heat rate, the net heat inflow or outflow for that grid cell. All right, and actually all the grid cells. So we ultimately need to calculate this for all the grid cells, but I was just referring to only one grid cell. All right. So here so as I said, this was the last term, which was the conduction term, and now in this way the energy conservation equation is written. All right, and now it's time to add the boundary conditions. And as I said before, we have only wells for this porous medium. What we have done here is to calculate the pressure of the production well at the location of the perforations, and then we use this pressure at the perforation to calculate the production rate, which is the mass rate of the production well, and we add this to the pressure equation of the production cell plus the mass rate of the production well. All right, great. So you might be wondering, even though we are producing fluid from that grid cell, why do I add this value to the pressure equation? Because when we usually talk about fluid production, we do subtraction. We subtract the equation. We subtract the mass that is produced from the equation. But if you actually take a look into this residual equation, you'll see that this is the accumulation term, which is the left-hand side of the equation, and the right-hand side of the equation is this, which is moved to the left-hand side of the pressure equation. And so on the right-hand side of the pressure equation, this term has a minus sign, but because now it's moved to the left-hand side, it has a plus sign. And the same thing occurs, and the same thing happens to the boundary conditions. Boundary conditions are added to the right-hand side of the pressure equation, but because we moved all of them to the left-hand side of the equation to write these residual equations, we need to change the sign. All right, and that's why for the production rate, we use plus values, and for injection rates, we use minus values. All right, we use minus values for injection rates. For production rates, plus values. Because we moved this term from the right-hand side of the pressure equation or the energy conservation equation to the left-hand side, and that's why the sign changes. All right, so great. We talked about this. This is for the pressure equation. We also need to add the boundary condition of the injection well to the pressure equation in this way. We have the volumetric rate of the injection well specified by the user. We multiply it by the density of the injected fluid. And so the mass rate of the injected water is calculated here, and we subtract it from the pressure equation of the injection cell. Now we're done with the pressure equation. Now it's time to add the required boundary conditions to the energy conservation equation. In this way, for the injection well, we multiply the volumetric injection rate by the density. So this is actually the mass rate of the injection well, and we multiply the mass rate of the injection well by the specific enthalpy of the fluid that is injected into the porous medium. And for the calculation of the enthalpy of the fluid injected into the porous medium, I used the temperature of the fluid injected into the porous medium, which is specified by the user, and the pressure of the cell in which the fluid is injected. Why did I do this? Because I don't have the bottom hole pressure directly. So I thought that maybe it is a simpler idea if I use the pressure of the cell in which the injection well is located instead of calculating the bottom hole pressure of the injection well in a different way. All right. So in this way, we calculate the energy rate of the injection well, and we subtract it from the energy conservation equation of the injection cell, and we do almost the same thing for the production well. We have the mass rate of the production well, we multiply it by the specific enthalpy of the fluid that is being produced from the cell in which the production well is located. So we calculate the energy rate of the production well in this way, and we add this value to the energy conservation equation of the production cell. All right. Now that we are done with writing the energy conservation equation and the pressure equation, and in other words, the governing equations that we have, now it's time to do the same thing that we did before. We collect all the equations this way, and we do the same thing. I'm not going to talk about them again. And in this way, we calculate the new pressure values and the new temperature values, and these values may be used again. And if the tolerance is satisfied, we consider them as the solution of the time step. And in that case, if that is the solution of the time step, the values will be stored in this struct, and after all the time steps are solved, we exit the main for loop, and then we will have all the solution, and then we can see what the results look like. All right, so let's see what's going to happen. If you run this on your own computer, it'll be certainly faster than this, because now the video recorder is running, and it certainly reduces the speed of the program. All right, so let's see what the results are going to be. And we will have two figures. One shows the pressure distribution in the porous medium, and the other one shows the temperature distribution in the porous medium. In this case, because we have a one-dimensional porous medium, I can use the word profile. So we will have a pressure profile and a temperature profile for our porous medium to see. All right, so let's see what they look like. All right, so these are actually the final solution of the problem. As you see, this is the injection well, production well. The pressure has increased on this side of the porous medium, and as the pressure increases, the enthalpy increases, and that enthalpy increase results in a temperature increase. And that temperature increase is observed here, but ultimately the effect of the injected cold fluid actually is shown here. And as you see, the temperature of the fluid has dropped to, from 300 degree 300 Kelvin to this value. And as you see, it has also increased to about 305 Kelvin because of the pressure increase. All right, and we also have a little bit of temperature reduction because of the pressure reduction near the production well. All right, because when the pressure drops, the enthalpy is reduced, and when the enthalpy decreases, the temperature drops. And we can see that temperature reduction near the production well. All right, I think that was all the things that I was going to talk about, and I hope that you learned something and you can use it for your own purposes, and even make it more advanced and add some features to it, change the boundary conditions, change the properties, and do it in any way that you think it's going to be more practical and more efficient. All right, thank you so much. Thank you for watching this video, and I hope you're having a great time.